So what are the usual vector operations? We know vector operations means we know that we have like R2 in R2 and C2 you have whatever you have in R2 and C2, the same kind of vector operations like addition and scalar multiplication is there in Rn and Cn as well, right? So scaling and addition, right? So and what is linear combination? Linear combination is, suppose you have two vectors, then C1v1 plus C2v2 is a linear combination of v1 v2, right? So same way you see that if you have many vectors, then you are going to write a1 v1 or alpha 1 v1, alpha 2 v2, alpha 3 v3, like this you are going to write. So that is the linear combination of any given set of vectors. Okay, now can you tell what will be the set of all linear combination? That is called the span, right? The collection of all linear combination of a given set of vectors is called the span of the set of vectors. So the span of the vectors is usually called, what is the span of the, suppose let us say you have only one non-zero vector, particularly from R2, how do you call the span of the vectors of the vector non-zero vector? One non-zero vector from R2 I am telling, suppose you are having one non-zero vector from R2, what is the span of that vector? No one? You are having one vector AB, and span of that one vector is the line through origin and AB, right? You forgot, I guess, or I don't know what is the situation. Okay, so the span of one non-zero vector is a line through the origin and that point. Okay, and here a comma b is some point which is not the origin, so a comma b is a non-zero point. So if you just take the zero vector and take the span, it is a zero vector. Okay, fine. Now here you see that span of three vector definition is given. In general, what is span of a set of vectors? Span of a set of vectors is the collection of all possible linear combination of those vectors. Okay. So what are some properties of span? We know span of v1, v2, v3 and so on is same as span of a v1, v2, v3. Right. So even if you multiply a scalar, vector with a scalar, then the span is not affected. Right. Also, if you add a scalar multiple of a vector to another vector, then also the span is not altered. Okay. So these are some properties of span. Okay. So here you see, we have done some row operations. The row operation is not affecting the span at all, right? First of all, what do you know about this span of this particular set? First tell me that. Hold on. I am not able to find the pen option. It's usually in the insert. Okay, it has come here now. Setting. This is not my usual pen. Please hold on. There are some changes in this, I guess. Hold on. I'm looking for the usual pen I use. Oh, I have opened the doc file instead of PDF. That's why. Please hold on. So now you see that what is the span of 1001? Can you tell me? What is the span of 101?
Entire R2.
What is the span of 1001? Can you tell me?
Entire R2.
Yes, it is R2, right? So span of 1001 is R2. So now you are having a different set of vectors 1, 2, 2, 5 and 3, 8. Now what is the span of this set we want to see? So for this what we are doing the row reduction, right? We are doing the row reduction. So when we do the row reduction, what is the last step here? So here you are actually, if you, there is one more step if you want to do. So if you do the last step here, so let us say you do V2 V1 with V1 minus 2 times of V2, then you will end up with 1001 and 00, right? So span of 1 to 2538 is same as 1001. So it means the span of this set of vectors is just R2, exactly same as this. Okay, now here what do you see? You have 1 2 2 4 3 6. What is that immediately we can observe? If this is v1, if this is v2, and if this is v3, then you know that v3 is 3 times of v1 and v2 is 2 times of v1, right? They are all multiples. So what happens in this case? You have, so you have only one particular row. So if there is only one row, I already told you span of one non-zero vector is a line through the origin and that point. Okay, so either it is the entire R2, if it is the, except for the zero vector, so either it can be span of zero vector is the zero, just the zero vector, and span of one non-zero vector means you know that it is a line through origin, and span of a given set of vectors where you have at least two linearly independent vectors, then you see that the span is R2. Okay, fine. Now, so you know these are the possibilities. So one non-zero row or two non-zero rows. So in one non-zero case, this is the scenario, and two non-zero rows, you will get the entire plane in R2. Okay, fine. So what is the general case then? The general case Fn. So F represents, you know that it is either R or C, right? So here you take a set of k vectors v1 v2 vk, and each of this vector is from Fn. Okay, the linear combination of the vectors v1 v2 vk for scalar c1 c2 ck in a field F is a new vector. What is that? So it is nothing but the c1 v1 plus c2 v2 plus etc ck vk, right? So this is the usual way we do in R2 as well, right? And span definition also goes exactly the same way, just like in Fn. Okay, so span of v1 v2 vk is the set of all possible linear combination of v1 v2 vk. Okay, and now what is a subspace of Fn? A subset S of Fn is a subspace if it satisfies this condition, that uv is in S, and for any scalars in F, au plus bv is in S. Okay, so it is closed for any linear combination. Okay, so always remember that span of any set of vectors, even if it has a non-zero vector or zero vector or whatever it is, span of any set of vectors is always a subspace. Okay, remember this, this is important. So span of any set of vectors is always a subspace. Okay, you don't have to verify any condition for this. Straight away, if you have span of some set of vectors, you can straight away tell that it is a subspace. Okay, so what are some important points here? A subspace must contain the zero vector, so it is closed under addition and closed under scalar multiplication. So these are the important points about a subspace. Okay, fine. So now let us look at what are linearly dependent and independent vectors. Okay, so this is a very important topic. So first topic is that what are linear combination and span we saw. The next topic is subspaces, and now we are going to see linearly dependent and linearly independent set of vectors. Okay, first of all, can you tell me if two vectors are linearly dependent? Let us say you have two vectors v1 and v2. When do we say that they are linearly dependent? What is the immediate way to check whether two given vectors are linearly dependent or independent? They should be
Ma'am,
multiples of each other for linear dependency, right? So if v1 is equal to alpha times of v2, then they are linearly dependent. Then they are multiples of each other. Here, if two vectors are linearly dependent, it means that they are multiples of each other. All right. Okay. Now, if suppose you have a set of vectors and one of them is 0, so is the set linearly independent or dependent? The set is linearly dependent, right? The set is linearly dependent. Okay. And any superset of a linearly dependent set is linearly dependent, right? It means what? Suppose you have a set A which is linearly dependent, and you have another set B which contains A, then B is also linearly dependent. Okay. So what is linear? The exact definition, if you want to see. So if we are able to find some scalars, at least one of them should be non-zero, such that a1 v1 plus a2 v2 plus etc. an vn equal to 0, then we call this set of vectors to be linearly dependent. Okay. So at least one of the coefficients. So at least one of the coefficients must be non-zero. Okay. Fine. And the opposite of linear dependence is linear independence, right? So if you take any linear combination and equate it to 0, then the coefficient should definitely be equal to 0. Okay. So only possibility when the linear combination equated to 0 is when all the coefficients are 0. So that is linearly independent set of vectors. Okay. So a subset of a linearly independent set is always linearly independent. Okay, fine. So now just looking back here, so can you tell me whether v1 v2 v3 are linearly dependent or independent?
dependent.
Yeah, linearly dependent, right?
Dependent.
Yeah, so this set of vectors here, they are linearly dependent. What about this set v1 v2 v3?
Linearly dependent.
Again this is also linearly dependent. Why?
Because three vectors in R2 will
Yeah,
be linearly dependent.
so more than two vectors in R2 is always linearly dependent. Now suppose I am picking any one of this set v1 v2 or v2 v3 or v1 v3. Now what can you say about each of this set individually? What about v1 v2 first of all? Are they multiples of each other? They are
No,
not
ma'am.
multiples of each other, so it means it is linearly independent. Same way you can see that this is also linearly independent, this is also linearly independent. Okay, fine. So already I have told you span of one vector means, so if it is in R2 it is a line, right, in general, or if you have one particularly non-zero vector, so if it is the zero vector, so span of the zero vector if you are taking, then you will simply get 0, right? And if you are having span of one non-zero vector, then it is simply alpha v, right? And span of two vectors means you will have all possible linear combinations, right? So span of uv, okay, so it depends on whether it is linearly dependent or independent. Suppose it is linearly independent, in that case you will see that it is alpha u plus beta v, where alpha and beta belongs to f. Suppose it is linearly dependent, then you can choose any one vector, right? And you write alpha u, alpha in r, or you can alpha in f or r depending on the situation, or You can write alpha V, alpha in F. Okay. So in independent case, this will be the scenario, and dependent case, this is the scenario. Okay. Fine. So, okay, I have given the cases separately, but anyway, I wrote it here. Okay, I could have written it here, but anyway, I have written it here. Okay, fine. So suppose we have more than two vectors in Fn, how to check linear dependence? Okay, so in that case, so one thing we can do without this elimination, what is that? Suppose we are having a set of n vectors in Fn. Okay, first of all, let me say, suppose you have two vectors, or let's say three vectors in F3 or R3. How will you check linear independence? Can anyone tell me? How will you check? Suppose you have three vectors in R3, V1, V2, V3. How will you check they are linearly independent or not?
One way is to find out rank.
Okay, can you find it? Yes, rank is one way. Is there any other method? Okay, so can you tell using determinant how can we tell linear dependence or independence?
If determinant is non-zero, then it will be
Exactly.
linearly independent.
So you write the vectors as columns. Okay, so V1, V2, and V3. You write the vectors as columns of a matrix. If the determinant is non-zero, then the vectors are linearly independent. If it is zero, it means it is linearly dependent. Okay, non-zero means linearly independent. Okay, also if you are using rank, what should be the rank of this matrix?
3.
3. So if rank is 3, then you know that it is linearly independent. Okay, but suppose in case instead of 3 vectors, let us say you are having 4 vectors. Okay, then how will we know how many linearly independent vectors are there? Okay, in that scenario, you have to use elimination method. Okay, you have to use row reduction and make the matrix look like this. After row reduction, if there are any 0 rows, what does it mean if there are 0 rows?
Linearly dependent.
Yes, if there are any 0 rows, then it is linearly dependent. If no 0 rows are there, then it means it is linearly independent. Okay, fine. So the number of non-zero rows here represents the number of linearly independent vectors. Okay, it is also the rank of the matrix. Okay, fine. So now you are having this problem. You are having a set of vectors here. Okay, now you want to see first of all they are linearly independent or dependent. So can you just by looking at this first of all tell me in which space do they belong? They belong to which space?
R3.
R3. They belong to R3. And how many vectors are there?
4.
4 vectors are there. So if 4 vectors are there in R3, can you tell the answer straight away?
Linearly dependent.
Linearly dependent.
Yes, it is linearly dependent. But how many linearly independent vectors are there? How to do that? So we are going to write the vectors now here as a column of a matrix. And we have to do row reduction and see how many non-zero rows are there. Now, is this form in already in row reduced form or not? Is it in this format? Yeah, it is in that format only, right? So you see in this diagonal you have 1 and below diagonal everything is 0. So you see that you are having a row reduced form already. So how many non-zero rows are here? It is already in reduced form. And how many non-zero rows?
3.
3 non-zero rows. So 3 non-zero rows means what is the dimension of that vector space?
3.
3, right? So here the dimension is 3. Okay, fine. Now let us look at the next case. The first case is clear for everyone, right? Why it is linearly dependent and why dimension 3. Yeah,
Yes.
fine. Fine. Now the next case is you have 1 0. So this is A. So the next case is you have 1 0 minus 1. You have minus 1 2 0 minus 2 0 0. Okay, so this is the matrix you have. Now we have to either find the determinant or we have to find the row reduced form. So you can try in both ways. So one easy method I see is that if you interchange column 1 and column 3, what will happen? You will get minus 2 0 0, minus 1 2 0, and 1 0 minus 1. Now you divide each of the columns by the corresponding numbers, like R1 replaced with R1 by minus 2, R2 replaced with R2 by 2, and R3 replaced by minus R3. So in each of these cases, you will see that you will just get 1 1 1. So how many non-zero rows you see in this matrix?
3.
Again you see 3 non-zero rows. Right? So are they linearly dependent or independent?
Independent.
Independent. So this is linearly independent. And the dimension is again
3.
3. Right? Okay. Now for C, so let us say this is V1, this is V2, and this is V3. Can you observe something straight away? Your V2 is
Minus V1.
and your V3 is.
2 times V1.
So what is that you see? They are multiples. So is it linearly dependent or independent?
Dependent.
Dependent. Okay. So now what is the dimension?
1.
1, because all are multiple of only one vector. So it is linearly dependent and dimension is 1. Why the dimension is 1 is clear, right? Because you have the other two vectors, both are multiple of the same vector. Okay, fine. Now in the next case you have V1, V2, V3. Now what do you observe? What do you observe? Can you write V3 as a linear combination of V1 and V2? Is it not straightforward?
Yes, ma'am.
What is that?
V3 equals to V1 minus V2.
Yeah. Okay, V1 minus V2. So you see that the third vector is a linear combination of the other two. So is it linearly dependent or independent?
Dependent.
Yeah. Okay. So it is linearly dependent, and what is the dimension in this case now?
2.
2. You have two linearly independent. You see V1 and V2 are not multiples of each other. So you see the dimension is 2. Okay. So all the subsections here are all clear to everyone. Finding the dependency or independency and then finding the dimension. Both the part clear, right? Good. Okay. So if V is the subspace spanned by the two vectors minus 1 0 1 2 1 minus 1 in R3, then which of the following vectors belongs to the subspace V? So first of all, what is the span of these two vectors? So V is span of minus 1 0 1 2 1 minus 1. According to the definition, it is alpha times minus 1 0 1 plus beta times of 2 1 minus 1, where alpha and beta are real numbers. Now this is nothing but minus alpha plus 2 beta, right? and this is just beta, and then third place you have alpha minus beta, alpha beta in R. Now suppose I am replacing each of this with xyz. What are the conditions I have on xyz? The very easy thing, you see that, okay, minus alpha plus 2 beta is your x, your beta is simply y, and alpha minus beta is z, right? So now what is that you can observe? What is x? Suppose let me say this is equation 1, equation 2, equation 3. So what is 1 plus 3 giving you? Yeah, if you do 1 plus 3, what will you get?
Beta equal to x plus and y equal to x plus.
X plus z, right? So now using 2, so using 2, you know that y is equal to x plus z. It means you have x minus y plus z equal to 0, right? So x minus y plus z equal to 0. So this is the plane equation of the plane spanned by these two vectors. Okay, so this is the equation of the plane. Now let us see which of these vector belong to this. Okay, how to check? 1 1 0, does it satisfy the equation? So this is your x, y, z. What is x minus y plus z?
0.
Yes, x minus y plus z. 1 minus 1 plus 0 is 0. So this vector belongs to the subspace. What about 5 2 minus 3? 5 minus 2
0.
minus 3. But 5 plus, yeah, 5 minus 2 minus 3. Is it 0? Yes. What about the third one? 8 minus 5 minus 4.
-1.
So now this does not belong to the space. What about minus 3 0? Again minus 3 plus 0 plus 3. What is answer?
0.
0. So again this belongs to the space. What about the last one? So you have minus 5 by 6 and again minus 5 by 6 plus 5 by 6, which is 5 by 6. Again it is non-zero. So this does not belong to the space. Okay. So the vectors of only which satisfies this equation are there in this set. Okay, is this, do you all understand this problem? How we are checking whether the given vectors are there in the span of this set? Yeah, is it clear? Okay, fine. Okay. So the next topic is what is a spanning set, right? So we know what is meant by span and what is a subspace, right? So now a spanning set is a set of vectors which spans a given subspace. That's all. Okay, suppose you have a space S and you have a set of vectors v1 v2 whose span is equal to the subspace, then this set of vectors is a spanning set of S. Okay, now if the spanning set is linearly independent, then we call it a basis. If the spanning set is linearly independent, then it is called a basis. And what is the important property about basis? Every basis contains the same number of vectors. So here you see, we saw some examples here, right? So you see this is a spanning set for R3. This is also a spanning set for R3, right? So you see both of them are spanning sets for R3. So A, B, both are spanning set of R3, correct? Because the span of this set of vectors forms your entire R3. But which one of this is the basis of R3? A or B?
B.
Which one?
B.
Yeah. So you see that A is not a basis, but B is a basis for R3. Okay. So a spanning set which is also linearly independent is a basis. Okay, and spanning set need not have the same number of vectors, but if you take any basis, then it should be having the same number of vectors. Spanning set can have different number of vectors. Okay, fine. Now what is the dimension? The number of elements in a basis is called the dimension. Okay, so dimension of S is always less than or equal to n. So which n we are referring to? So here S is any subset of Fn, and this n represents this n only. Okay, so dimension of any subspace is less than or equal to n. Okay, so we cannot have more than n linearly independent vectors in Fn. That's why the dimension is always less equal to n. Okay, fine. So any vector space which has a finite spanning set is a finite dimensional space. So here in this course mainly we are concentrating on finite dimensional spaces. Okay, any subspace S of Fn can be written as span of a set of vectors. Okay, where v1, v2, vk are linearly independent and k is lesser equal to n. So what is the dimension of this subspace? So here v1, v2, vk are linearly independent. So S is the span of this set of vectors. What is the dimension of S?
K.
K.
K. So the set forms a spanning set or basis for S.
Basis.
Actually, it is a spanning set and
Also a basis.
yes. Okay. So the dimension is K, and here it is a basis. So basis implies that it is also a spanning set. Basis implies already that it is a spanning set by definition, right? Okay. Now what is that you should know? Suppose you have a set of m linearly independent vectors and you have a k vectors of set of k vectors which is spanning, then you should always know that this m is less than or equal to k. Okay, so you can always say that any spanning set, the limit here is that linearly independent set, the limit is m is less than or equal to the spanning set. Why is that so? You saw this example, right? So here the spanning set can have more than 3 vectors, but minimum you need at least 3 vectors. Minimum you need 3 vectors, right, for a spanning set. So you see that here 3 is less than or equal to 4. The same concept here. So you see that if you take any linearly independent vectors, you know that that should be less than or equal to the size of any spanning set. Okay, fine. So for finding a basis, you basically do the elimination process, and whatever vectors you obtain in this process, they form a basis, right? So for example here, yeah. So for example here you see in this set, you have a set of vectors. So how do you find a basis? Even here also, how do you find a basis? So you do the row reduction. Whatever vectors you are obtaining at the end, that will give you a basis. Okay, here if you reduce it further, you will get a basis, right? Okay, now consider this example. How do we find the basis for this? How do you find a basis for this? Okay, so suppose let us say you are having W is equal to set of all x, y, z such that x plus, very simple example I am taking. What is the basis of this subspace? How will you find? What is the basis?
Using canonical form.
Do you really need canonical form here? Is there any other method? Why? How will you first of all use canonical form here? I don't know what do you mean by canonical form. Canonical basis is there, but I'm asking if you're given a specific subspace, how will you find the basis?
Yeah, take any two
Yes.
values and
Yes. So I understand your idea. So what he is saying is that, so let us fix one of this variable. Okay. So suppose I am fixing z, then z I can write as minus x minus y. Right. So you have x, y, and in place of z you have minus x minus y, right? So now your x and y are in R. Now I can take this x and y commonly. So here I will get the first coefficient is 1. For x second it is 0, and for third it is minus 1. Plus y times of 0, 1, minus 1. X, y in R. Right? So you see 1, 0, minus 1, 0, 1, minus 1. This forms a basis of W. Okay, so this is how we find basis. Now can you tell me how do we find a basis for this space? So we have to do the same thing. You have an equation, we are going to fix one of them and rewrite this set here, right? So now W is equal to, instead of x5 you have minus 2 by 3 x1, and same way instead of x4 you have minus 4 x2, right? So the given set can be rewritten as x1, x2, x3, instead of x4 minus 4 x2, and instead of x5 minus 2 by 3 x1, right? Your x1, x2, x3 in R. Right? So now you see that we can take x1 commonly. The coefficients are 1, 0, 0, 0, minus 2 by 3. And x2 if I take commonly, it is 0, 1, 0, minus 4, 0. Alright? And here if I am taking x3 commonly, you will get 0, 0, 1, 0, 0. Okay, so you have x1, x2, x3 in R. Okay, so you see these three vectors will form a basis. Now can you tell me, so let us call this vector v1, v2, v3 as a basis. Now I am going to write another set. Let us say 3, 0, 0, 0, minus 2. 0, 1, 0, minus 4, 0. And 0, 0, here I am going to write 100. 0, 0. Is this also a basis?
Yes.
Right? So if you do scalar multiples, so for the first vector I have replaced with 3v1, here I have replaced with 100v3. So this is also a basis, right? This is what we saw. So like span of the properties of span in the very beginning we saw. So because of this property, you see that this particular set which I have written is also a basis. Okay. So sometimes the basis there are infinitely many bases for a given space. Non-zero, any non-zero subspace has infinitely many bases because of this property. Okay. So if you are given a multiple choice question, okay, you have to make sure that you try even if you find basis like this, you have to check that any multiples or linear combinations are there. You cannot fix one particular basis for a subspace. Keep that in mind. There is not a fixed basis for any non-zero subspace. Keep that in mind. Okay, fine. Okay, so now the next topic here is what are linear transformations. A linear transformation T from Fn to Fm is a mapping that associates every input, so every element in Fn to an element in Fm. How does it map? What is the condition you need? So T from C, so T of Cu should be C times of Tu for any scalar C and vector U in Fn, and T of U1 plus U2 is T of U1 plus T of U2 for any two vectors in Fn. Okay, so if any mapping satisfies this condition, then we call it to be a linear transformation. Okay, so here can you tell me what is the domain and codomain for this first one? What is the domain and codomain for the first one? T is from which space to which space?
F4 to 3.
Okay, so maybe I will write R4 to R3 or R2.
Yeah, R2.
Okay. Now what about the next one? T is from,
R4 to R3.
okay, fine. Okay. So now what will be the size of the matrix representation? So you know that if T is from Fn to Fm, what is the size of the matrix representation?
M cross N.
Yes. So matrix of T is an M by N matrix. Right? So here in this case, for the first one, what should be the size? This is 2 by 4. And what about the second one?
3 cross 4.
Yeah. Okay. So now how do you write the matrix representation? For this, if you are not given any specific basis, then we are going to use the canonical basis. So if we are using the canonical basis, first we will find what is T of 1, 0, 0. What is T of 1, 0, 0 for this case? 1, 0.
1 0.
What is T of 0, 1, 0, 0?
0 1.
0, 1. What is T of 0, 0, 1, 0?
1 1.
1 and 1. What is T of 0, 0, 0, 1?
-1 and 5.
Yes. Okay. So your matrix, always remember, you should have TE1 here, the coefficients of TE1, TE2, TE3, TE4. Always write the step so that you don't miss it. Write the column titles. So even if you have a different basis, you will not mess up. Okay, so here you see TE1 is 1, 0, TE2 is 0, 1, TE3 is 1, 1, TE4 is -1, 5. So this you see that it is a 2 cross 4 matrix. Okay, clear? So same way, let's do the next one. What is T of 1, 0, 0, 0?
1 0 -1.
T of 0, 1, 0, 0 is
2
2
1
1 minus 5.
2, 1, -5. What is T of 0, 0, 1, 0?
3 2 0.
What about the last one? T of 0, 0, 0, 1?
0 5 1.
0, 5 and 1. Okay, so your matrix of T, T1, T2, T3, T4. The columns are 1, 0, -1, 2, 1, -5, 3, 2, 0, 0, 5, 1. So you have a matrix of size 3 by 4. 3 cross 4 matrix you have. So the matrix representation for any transformation, is it clear for everyone? Yes? Okay. Now suppose you are given the matrix and you are asked to find the transformation. How will you do? The other way around. How will you do? So suppose you are given this matrix only and you are asked to find what is the transformation. How will you do? You will simply multiply this matrix, right, with x1, x2, x3, x4, right? So you simply have to multiply x1, x2, x3, x4. So if you multiply, what will you get? X1 plus x3 minus x4. See? And then x2 plus x3 plus 5x4. Okay. So transformation to matrix or matrix to transformation, you should be clear with both. Okay, fine. So here the next topic is what is the range of T and what is the null of T. Range of T, first of all, you see that this is a subspace of Fn. Sorry. So if T is from Fn to Fm, then range of T is a subset of Fm. And null of T is a set of all u in Fn, since the T of u equal to 0. So all the u from Fn only. So this is a subset of Fn. And both are subspaces. Remember, both are subspaces. Okay. So to find the range or null, do you need to look at the transformation or is it enough to look at the matrix representation?
Matrix representation is enough.
Matrix representation is enough, right? Okay. Now, what is the dimension of the range of T called?
Rank.
Rank. And same way, what is the dimension of null space of T called?
Nullity.
Nullity. Okay. So rank and nullity, this rank nullity theorem also called as the fundamental theorem of algebra. What does it say? Rank of T plus nullity of T is equal to n. Okay. So now for example, you consider this matrix. For this matrix, what is the nullity? So let us call this matrix to be A. Let us call this matrix to be A. What is the rank and what is the nullity? Rank of A is
2
2.
and nullity 0.
Yeah. Nullity is? See, what is the rank nullity?
Yeah, 2. Nullity 2.
Yeah, be careful. See, your T is from Fn to Fm, right? So you are having an M cross N matrix. So this N here represents the number of columns. Remember that your N represents the number of columns. Okay. So here, for this one, the nullity should be, the number of columns is 4. So nullity is 4 minus 2, 2. Right? Same way, what is the, let us call this to be B. Now what is your rank of B? So for this, actually you need to compute the row reduction and then you do, that is the better way, so that you don't make any errors. Okay. So maybe you try this as a homework, find the rank of this matrix. Now one small observation maybe we can say. So can you tell me what is the rank of, let us say you have any alpha non-zero. What is the rank of, maybe you take this A or any A. What is rank of alpha A?
Also 2.
Also 2 only, right? So multiplying by a scalar is not going to affect the rank of the matrix. Okay, one more question about rank. Let us say you are having an M by N matrix. What is the maximum rank of A?
N or less than n.
So you write it minimum of M comma N. Okay, rank of A is always less than or equal to minimum of N. For example, suppose you are having a 5 by 7 matrix. Your rank should be always less than or equal to, which one is the minimum value?
5.
5. So your rank should always be less equal to 5. So suppose you are having a 5 cross 3 matrix. Now what should be your maximum value for the rank? What is the minimum value?
3.
3. Right? So the maximum value is 3. Okay? Fine. So the maximum of rank of A is less than or equal to this. Okay? Fine. So now if rank is given, you know how to find the nullity. Right? So you know how to find the nullity. Suppose you are having, let us say, a matrix like this. Now for example, 3 cross 4 matrix is this. So what is the maximum possible rank? What is the maximum possible rank?
4, 3. Yeah.
The maximum
3.
possible rank is 3. So now what is the minimum possible nullity? So we are talking about maximum possible rank. So let me split it down here. So I'm taking this example or any 3 by 4 case. Okay, so your matrix is a 3 by 4 case. So you know that maximum rank is 3. So it can be either 2 or 1. So let us say A is a non-zero matrix, so it cannot be 0. So it is 3, 2, 1. Now, what is the minimum possible nullity? So you know that rank plus nullity should be equal to what? For this
Number of columns.
it should be equal to,
N. Number
so,
of columns.
yeah, so here it is 4, right? Here it is 4. So here, what should be, if rank is 3, what should be the nullity?
1,
1.
And if rank is 2, what should be the nullity?
2.
2,
And if rank is 1, what is the nullity?
3.
3.
3. So you see that the minimum nullity is 1. The nullity cannot be 0 in this case. Okay, so the nullity is greater than or equal to 1 in this case. So the minimum nullity means it is greater or equal to 1. So rank nullity theorem. So using this, you can say what is the maximum rank, and when you apply rank nullity theorem, you can say what is the minimum possible nullity as well. Okay, fine. Okay, so next we have week 6 topic. With this, we are done with week 5 topics. So in week 6, we are looking at linear operators. What are linear operators? What are linear operators?
And transformation from same vector space to same vector space.
Yes, so the domain and codomain are same, right? Fn to Fn, right? So in this case, the matrix representations are square matrices, right? Because n cross n, right? So they are square. So if you have square matrices, then you know that we can talk about inverse, right? So now suppose you have an operator T. When will the inverse exist? What is the condition for inverse? First of all, the definition is that so in terms of transformation, you use composition. So this is the definition: S composition T equal T composition S equal to I. This S is the inverse of T. Now suppose we are talking in terms of the matrix, then you say that suppose you call A M of T is A, then the inverse is a matrix satisfying this condition: A inverse A equal to A inverse equal to I, right? The matrix multiplication, right? So now what is the criteria for the matrix to have an inverse? So
Determinant is null.
yes, so you, in terms of determinant, suppose this is an n by n matrix. What are all the equivalent condition for existence of inverse? Let us write it down. The determinant should be non-zero. What can you tell about rank?
Rank should be
Rank should be maximum.
N. And what should be the nullity?
0.
0.
Nullity is 0. Right? So these are some equivalent conditions. Or let us say how many linearly independent rows or columns are there for A?
N.
That also should be n. Okay, so these are some equivalent conditions for inverse existence of inverse. Okay, fine. Now, yeah, invertibility if and only if null of t equal to 0. Yeah, one more equivalent condition is there. I missed this one. So nullity is 0, rank is n. We have seen n columns linearly independent. We've seen the third one I missed. You see, mx equal to 0 has a unique solution. So this system of homogeneous equation has a unique solution. So this is a kind of equivalent to saying the null space is 0, right? This is equivalent to saying null space is 0. Okay, fine. So this is other way to say that null space is 0. Okay. So here are two matrices. Do you know how to find the inverse? What is the technique you use to find the inverse?
Take this matrices and make a augmented matrices with identity
Yes.
operator,
Yes.
and then apply uh, reduce row echelon form.
Okay. So first of all, find the determinant of both the matrices. Okay. So first step is that find the determinant. What is determinant of A? What is determinant of B? Only when the determinant is non-zero, you know that the matrix is invertible, then you do the next step. So you find the determinant. If the determinant is non-zero, then what will you do? You write the matrix, augment it with the identity matrix, then you perform the row operations. Okay, so everyone do this. Within 5 minutes I'll be back. By then you should have at least the answer for the first question. Okay, everyone do this, find the determinant and then proceed with this step. Okay, do this. Did you find the determinant? What is the determinant of A? What is the determinant of A?
7.
7. So I don't know whether your answer is correct. What about the others? Did anyone else also try the determinant?
-9 maybe.
-9. So let me see one. Quickly let me do. So the determinant is 1 minus 1 minus 2 times of 2. So only this much is there, and this is becoming 0, right? So 0 minus 1, and for this only you have 4. So -1 minus 4, actually it's minus,
-5.
yeah. So is it invertible?
8.
Yeah.
Yes.
And what about B? What about B? For B, it is 1 times of -2 minus 2 times of again 4. Correct? 1 times of -2 and 2 times of not 4, 2 only. Sorry. 2 times of 2. 2 minus 3 actually. 2 times of 2 and then -3. So you have -2 plus 2, 0. So A is invertible and B is not invertible, right? So this is invertible and this is not invertible, right? So this is a singular matrix. So we can find the inverse of the first one, right? So now we have to do all the step-by-step process for finding the inverse. Everyone try this. How will we find?
Ma'am,
Yes.
ma'am, in determinant there should be 4, na? -2 multiply 4.
Yes, ma'am.
Where?
In determinant, where you find the determinant of A, there should be na -2 multiply 4.
-2 multiplied with, yes. Sorry, here also I made a mistake. 4.
Yeah, that's why it's -9.
Yes, correct. So now it's -8 and so it's -9. Yeah. Okay, fine. All right. So now you see that this is non-zero, so the determinant inverse exists. So the next step is that we have to find the inverse. So how will you row reduce? How will you do the row reduction? The first one is already 1 for us. So the first row, we don't have to do anything. Now the operation is for the second row. So for the second row, which operation we can do? Row 2 replaced with row 2,
2 minus 2 times row 1.
row 1. Right? So what is that we will get? We will get 1, 2, 0, 1, 0, 0. And then for the second one, this becomes 0. And what happens here? 0 minus 4. So this is -4. And then here 1 minus 0. So it is 1. What about here? 0 minus 2. So -2. And then here 1 and 0.
0.
Is that correct? Yeah. And then the next row will remain the same. 0, 0, 1. So the next step is that we have to multiply the second row with -1/4, right? So the next step is R2 replaced with -1/4 R2. So what is that you will get? You will get 1, 2, 0, 1, 0, 0, 0, 1, -1/4, and here 1/2 -1/4, 0. Fine. And then the last step is 0, 1, 2, 0, 0, 1. Now what is the row operation we need to do next? R3 replaced with R3 minus R2. Right? So R3 replaced with R3 minus R2. So you will have 1, 2, 0, and then you will have 1, 0, 0 here, and then 0, 1 minus 1 by 4, and then here you have 1 by 2 minus 1 by 4, 0, and here 0, 0. What is 2 minus 1 by 2 plus 1 by 4 actually, right? What is 2 plus 1 by 4? You will have
5/4.
9/4.
9 by 4, right? 9 by 4, and then here you will have R3 minus R2. So minus 1 by 2, 1 by 4, 1. Right? So this is what you are having here. And then you have to replace this 9 by 4 now. Right? You have to make this 9 by 4 as 1. So what is the next step? The 9 by 4 you have
Divide,
to, yeah,
multiply by 4/9.
yes. Sorry, R3 multiplied by 4 by 9. So you will get 1, 2, 0, 0, 1 minus 1 by 4, 0, 0, 1. And here you will have 1, 0, 0, 1 by 2 minus 1 by 4, 0. And when multiply with 4 by 9, you will have minus 2 by 9. Here 1 by 9, 4 by 9. Correct? So now we have to make this entry 0. How can we make this entry 0?
R1 minus 2 times R2.
R1 minus 2 times of R2. Right? So R1 replaced with R1 minus 2 times of R2. So here what will you get again? 1, 2, not 2, 0. And here you will get minus 2 times of R2 means you will get 1 by 2. Correct? So 0, 1 minus 1 by 4, 0, 0, 1. So again here R1 minus 2 times of R2. So you will have 1 minus 1,
Minus 1.
so 0, 1 minus 1, right? So 0. And here this is again 1 by 2, right? 0 minus 2 times of this, and then here again 0. The remaining things will same. What about the next step? What is the next step? What is the next step? So you have to make this entry 0,
0.
entry 0. So I will just write the steps. You do that. So you have to make R1 as R1 minus 1 by
Minus 2 times R2.
R3, right? To make this 0. Right? Otherwise, if you do use R2, then again there will be a change. You have to use R3 here. And same way for R2, you have to do R2 minus or plus 1 by 4 R3. So if you perform both, then you will get the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Maybe you can fill this last step alone. Okay? Complete it. Okay, so only this part you need to do, complete it, you will get the inverse. So finding the inverse, how do you do? Is it clear? So you augment the identity matrix, you do the row reduction till you get the identity on the left hand side. Okay, and whatever matrix you get here, that will be the inverse of your matrix. Okay, is it clear how to get the inverse? Okay, fine. All right. Okay, so the next topic here is eigenvalues and eigenvectors. So what are eigenvalues and eigenvectors? So for first of all, eigenvalues and eigenvectors, we talk only for operators. So if you have an operator T from Cn to Cn, right, and any vector V satisfying the condition TV equal to lambda V for some lambda in C, that lambda is called your eigenvalue and the corresponding V, non-zero V, that is important. Your V should be non-zero. That non-zero V is called your eigenvector corresponding to lambda. Okay, so this non-zero is important. Okay, fine. What are the eigenvalues of the diagonal matrix or triangular matrix? What are the eigenvalues?
Diagonal entries.
Yeah, so the answer is diagonal entries. Right? Okay, suppose, okay, so first of all, can we rewrite this like this? So null of T minus lambda I, if this is non-zero, then you can say that your lambda is an eigenvalue and all the elements of this null are the corresponding eigenvectors. So this is another way to define eigenvalues and eigenvectors, right? So here, if null of T minus lambda is non-zero, then this lambda is an eigenvalue and all the vectors in this null are the corresponding eigenvectors. Okay, now the question is, suppose your null of T is non-zero. What does that mean? Compare it with this.
Rank is 0.
Can you tell it in terms of eigenvalues and eigenvectors? Your null of T is non-zero. From that, you cannot conclude rank is 0, first of all. Here, the question is regarding eigenvalues and eigenvector. Compare it with this. What is your lambda here?
Ma'am, there must be a zero row, so
No.
we cannot calculate the complete eigenvalues maybe.
No. See, null of T is nothing but null of T minus 0i. This is non-zero. So this means your lambda is 0. So it means you have 0 as an eigenvalue, right? You have 0 as an eigenvalue and you have some eigenvectors here. Whatever is there in the null space, they are your eigenvectors. So null of T. Vectors here are your eigenvectors. Okay, so this is the eigenspace, right? So whenever the null of T is non-zero, it means that lambda equal to 0 is an eigenvalue and everything in the null space is an eigenvector. Okay, so in this case, you already know that the rank is strictly less than n. If the rank is strictly less than n, you know that the determinant is 0, right? And what is the relationship between determinant and eigenvalues, by the way? If 0 is an eigenvalue, you know the determinant is the, what is the relation between determinant and eigenvalues? Very important relationship.
Ma'am, roots of determinant of A minus lambda I equals to 0.
See, the determinant of a matrix is equal to the product of the eigenvalues, right? Yeah. So the determinant is equal to the product of the eigenvalues. And if one of them is 0, it means the determinant is 0. Okay. So either way you can say, so you can use the rank and then say determinant is 0, or you can use the product of eigenvalues equal to determinant and then say the determinant is 0. Okay. So these are some observations. Okay. Now, so for every lambda in C such that T minus lambda is singular, so it means what? There exists some lambda means every operator has eigenvalues. So if it has eigenvalues, then obviously it has eigenvectors. Okay. So what is the formula for determinant is given here. Finding the determinant, I don't want to explain the formula. I guess all of you know how to find the determinant and all. Just tell me a few things. Determinant of a diagonal matrix is equal to product of
Diagonal entries.
diagonals, right? Diagonal entries. So the same is true for,
Upper and lower triangular matrix.
yes? Okay. So now, what are the other properties? Determinant of A is 0 if and only if A is singular. Determinant of AB is determinant of A into determinant of B. And the roots of determinant of A minus lambda I are the eigenvalues of the matrix A. Okay. So here is a simple question. Suppose A is an n by n matrix. What is the maximum number of distinct eigenvalues of A? What is the maximum number of distinct eigenvalues of A?
n.
N. Okay. So it can have maximum n distinct eigenvalues. It cannot have more than n distinct eigenvalues, right? Fine. So because determinant of A minus lambda I is a polynomial, right? It's a polynomial of degree n. So for a polynomial of degree n, it can have maximum n roots. It cannot have more than n roots. And those roots are your eigenvalues. That is why we can have maximum n distinct eigenvalues. Okay. So all the, as I already told you, all the elements in the null of t minus lambda I are your eigenvectors, or the non-zero vectors of null of t minus lambda I are your eigenvectors. And this null of t minus lambda I, this dimension for every eigenvalue, this dimension is always greater or equal to 1. So it means what? The null of t minus lambda I has at least one non-zero vector if lambda is an eigenvalue. Okay, fine. Now, what is algebraic and what is geometric multiplicity? Okay, so suppose let us say you are having a matrix and it is a 3 cross 3 matrix. Okay, so suppose the eigenvalues are 1, 1, 2. So what is the algebraic multiplicity of 1?
2.
It is occurring 2 times. Now, what is the algebraic multiplicity of lambda equal to 2?
1.
1. Okay. So, what is the geometric multiplicity of lambda equal to 1? Can we say without any calculation? It's not possible to say, right? Only we can say that it is less than or equal to 2. So, either it is 1 or it is 2. Only these are the possibilities. But can we say geometric multiplicity of lambda equal to 2? This we can say for sure. What is the answer?
1.
1. Because of two reasons. One, geometric multiplicity is always greater or equal to 1, and it is always less than or equal to algebraic multiplicity. So here also 1, here also 1, so it should be 1. Okay, so whenever the algebraic multiplicity is 1, automatically geometric multiplicity also becomes 1. Okay, so because of this relation here, this is an important relation for algebraic and geometric multiplicity. Okay, so based on algebraic multiplicity and geometric multiplicity only, we can say diagonalizability. What is diagonalizability? An operator T is said to be diagonalizable if there is a basis with respect to the matrix of T, where the matrix of T is diagonal. So if we are able to find a basis and the matrix representation with respect to that basis is diagonal, then we say that particular transformation is diagonalizable, or the corresponding matrix is diagonalizable. Okay, so usually the diagonalizability, we use the eigenvectors of T. Okay, so what is the criteria for diagonalizability based on algebraic and geometric multiplicity? What is the criteria for diagonalizability? Algebraic
Algebraic multiplicity should be equals to geometric multiplicity.
Yeah, for all eigenvalues of T, algebraic multiplicity should be equal to geometric multiplicity. If they are equal, then you know that it is diagonalizable. Even if for one eigenvalue, if this condition is missing, then you know that the operator is non-diagonalizable. All right. Okay. So what is this eigenvector independence property? So eigenvectors corresponding to distinct eigenvalues, they are always linearly independent. Okay. So whenever we have two distinct eigenvalues, then the corresponding eigenvectors are always linearly independent. Okay. So what is this is the condition we already discussed. So if T has n distinct eigenvalues, obviously n distinct eigenvalues means what is the algebraic multiplicity of each of the eigenvalue?
1.
So obviously the geometric multiplicity is
1.
1, right? So T is diagonalizable. More generally, if algebraic multiplicity is equal to the geometric multiplicity, then T is diagonalizable. Okay, so if geometric multiplicity is less than algebraic multiplicity for any eigenvalue, then you know that the operator is not diagonalizable. Okay, so these are the very basic things of diagonalizability. Okay, so you know if you have an operator, how to write the matrix representation, this we already saw. Now you have a matrix, find an eigenvector basis. So please don't be lazy, you are practicing for your exam, so solve this problem. Everyone find the eigenvalues and eigenvector. You may have done this earlier, but do this now because you are practicing for your exam. Okay, find the eigenvalues and eigenvectors for this matrix. Everyone do it.
Ma'am, this is a upper triangular matrix.
Are you sure?
No, sorry.
Okay, okay, carry on. If anyone finds the eigenvalues, let me know. Or you can put it in the chat also.
One, four, and minus two.
1, 4, and minus 2. Yes, correct. Good. So how many of you managed to complete the eigenvalues part? Please raise your hands. Only 2. What about the others? Have you not completed finding eigenvalues? Good. Rajkumar, Ashish, Akash, Aryan, Bhavya, Upendra, Divyanshu. It's like taking attendance. None of you have done this, completed this eigenvalues. Usually, Rahina is active. Today, complete silence. Yeah? Yash, Shivaraman, Shubham, Raman, Pranav, Mayank, Maki, Lucky. Completed or not? Finding the eigenvalues. What's the problem? So, what is the eigenvector corresponding to lambda equal to 1? So, the eigenvalues are 1, -2, and 4. So, what is the eigenvector corresponding to lambda equal to 1? So, how do you find it? So, you simply have to do a minus I. So, you will get 0, 0, 3, 0, 0, 0, 3, 0, 0. Very easy, right? And then you multiply it with x1, x2, x3 and equate it to 0. So, you will get x3 equal to 0 and x1 equal to 0. So it means you have 0, x2, 0. It means the eigenvector is 0, 1, 0. Right? So the eigenvector corresponding to lambda 1 equal to 1 is 0, 1, 0. Correct? Okay. What about for lambda equal to -2? Can anyone tell the answer for lambda equal to -2?
1, 0, and -1.
Yes. 1, 0, -1. Good. And for 4?
1, 0, and 1.
Good. Right? So what is your matrix S now?
First column will be 0, 1, 0. Second will be 1, 0, -1, and third will be 1, 0, 1.
Right? And what is your S inverse? You have to calculate, right? You have to calculate your S inverse, and what is your diagonal matrix? What is your diagonal matrix? 1.
At diagonal entries 1, -2, and 4, and others are 0.
Okay. So this is how you diagonalize a matrix, right? Okay. So the next part is that, so I hope everyone have a clear understanding about diagonalizability. If there are any questions, you should ask by now. And the next part is, how do you find the powers of a diagonalizable matrix? Suppose you know that a matrix is diagonalizable, then to find the power, you don't have to diagonalize the entire matrix. So, sorry, find the product of the entire matrix. You simply do the diagonalization, right? So you have D equal to S inverse AS. You simply do the rearrangement and then you will have A power M is equal to S times of D power M S inverse. So you simply have to calculate the powers of a diagonal matrix. How do you calculate the powers of a diagonal matrix? You take the powers for each of the diagonal entry, that's all. As simple as that, right? So A power m. So to find the power of A, you have to calculate S d power m S inverse. Okay, fine. So here, for example, this matrix also you can try computing the powers of A. So maybe this I'll leave it as a homework. You try computing maybe A cube from this. Okay, find A cube. Okay, fine. So what is this upper triangularization? Because all matrices are not diagonalizable, we need something which is not really like diagonalizability, but something better than the complete matrix, right? So that is upper triangularization. So what is this upper triangularization? So it means any operator, you take any operator, we can find a basis with respect to which the matrix of T is upper triangular. Okay, so we can, for any operator T, there is a basis with respect to which the matrix of T is upper triangular, right? So it means what? You will have, suppose you have an 3 by 3 matrix. Okay, suppose let us say it is not diagonalizable. Okay, so it is not diagonalizable. Okay, so not diagonalizable means, for example, let us say the eigenvalues are lambda 1 equal to lambda 2 equal to 1 and lambda 3 equal to 3. Okay, so let us say the geometric multiplicity of lambda equal to 1, suppose it is 1. Then what will happen? You will have only one eigenvector corresponding to this, right? So that you will write first. Okay, so that you will write first here. So let's say that one eigenvector is v1 and you will have an eigenvector corresponding to this. So now you have only two eigenvectors. So v1 and v2, these are linearly independent. Now you find a third vector, okay, which makes this a basis. This is any vector v3. V3 is any vector which just makes this set a basis. Okay, for example, suppose you are having 1 0 1 0 1 0, you need one more vector which makes it a basis. Okay, so you just have to find which vector. Maybe you have to try, maybe 1 1 1 means if you take, what happens, it is becoming a linear combination. So you have to try something different, 1 and then 1, something like this you see, and then whether it is a linear combination or not, you can check. So the third vector you have to find, just you have to randomly find a vector which is linearly independent and it forms a basis. So the third vector you are finding just from the other two vectors, it has nothing to do with the eigenvectors, right? So then what happens, you know that here this one will have entries only here, and this is 0 because you have tv1 equal to v1, some lambda times of v1. So here you have lambda 1 v1, and then tv3 is you have lambda 3 v3. So here you will have, so this v2 actually, right? So here 0, lambda 3, 0. And then what? The third one, you don't have any relationship like this. So you will have some vector here, right? So now we already have an upper triangular matrix for 3 by 3 case, right? So any 3 by 3 matrix just with a given set of vectors like this, it is easily doable. Suppose you have algebraic multiplicity 3 and geometric multiplicity 1, then what will happen? You will have only one eigenvector and you will have an eigenvector here. You have some vector here and some vector here. Then what you have to do? Then you have to take only this part and then do the triangularization again. Okay, so triangularization, don't worry, this is the process. Everyone should just know that at least every matrix is triangularizable. This much you should know. This is the process. Okay, Fine. And geometric multiplicity and algebraic multiplicity already we have seen. So algebraic multiplicity is the number of time lambda is appearing on diagonal, and geometric multiplicity is the nullity of m of t minus lambda. And we all know that geometric multiplicity is always less than the algebraic multiplicity. So these are some things we know. And what is the relation between the eigenvalues and trace and determinant? Determinant is the product of eigenvalues, and trace is what? The sum of the diagonal entries. Trace is the sum of the diagonal entries, and that is same as the sum of the eigenvalues. You see, the eigenvalues is linked so much with the determinant, trace, and everything, right? So determinant is the product of eigenvalues and trace is the sum of the eigenvalues. All right. Okay. So the last part here is what are circulant matrices. So circulant matrices are matrices which satisfies this condition. That is what? Suppose you have some row, then you just shift the row to one position. So you see this vector moves to the next position. Sorry, this entry moves to the next position and so on. And the last entry comes to the first position. The same way you do the shifting. Okay. So you keep on doing this shifting till you get a square matrix. So such matrices are called circulant matrices. How many of you checked the solution for this which I gave you along with the previous session's PDF? Did anyone check the solution I gave you? Good, at least one. Okay, so please check that. So I have given all the steps to find the eigenvalues and eigenvectors for finding the eigenvalues of a circulant matrices. Okay, so what are the topics we have in week 5 and week 6? In week 5, the first thing is understanding what are linear combinations, then span, then linear independence or dependence, right? Then subspace, dimension. When you talk about dimension, you should be able to find basis, right? And then linear transformation, matrix representation of a linear transformation, right? So once you have a matrix, you can find the rank nullity. And once you have rank nullity, you know what is rank nullity theorem. Rank plus nullity is equal to the number of columns of the matrix, right? So this is of week 5. And for week 6, what are the topics we see? In week 6, we have what are operators, what are inverse of an operator, how do we find the inverse, what are the criteria for the existence of inverse, right? And then what are eigenvalues and eigenvectors of an operator, what are algebraic multiplicity and geometric multiplicity of an eigenvalue, right? And then diagonalizability, what are the criteria for diagonalizability? If a matrix is not diagonalizable, we know that it is always upper triangularizable, right? And the final application is the circulant matrices. So these are the topics in week 5 and week 6. I hope we have covered almost all the topics today. So just go through all the notes. Okay. On Saturday, we will have a revision for week 7 and 8. Okay. Is it fine? All right. Just tell me one thing. So today, the way I have taken the revision session, I try to just have a view of all the topics.